All right, let me go ahead and start. Good morning, hello and welcome. So this week we are going to start talking about chapter 9, linear momentum. Just to put things in a perspective, let me just take a look back and remind you what we have done so far. So we are trying to describe motion, and we started with Newton's laws, right? We introduced things like F is equal to ma, and Newton's first law, no force means no change in motion. And we talked about things like I don't know, friction, circular motion, drag forces. And then later we introduced gravitation, and we said we could describe planetary motion with Newton's laws. And in the last 2 weeks, we started talking about a different way of looking at these things. Like, we didn't set up any forces, any free body diagrams. We were more like solving the problem by thinking about something called energy. And we said the energy was a fundamental quantity of the universe that was conserved no matter what. So this week, we'll also introduce something different. And I think most of you know this, but it's called linear momentum. And looking at problems from the momentum point of view also will simplify certain problems. Okay. So, okay, let me first introduce the momentum. Momentum, okay, I think it's easier to write what it is and then talk about this. And when we are talking about momentum, we are talking about linear momentum. In a week or two, we are going to be talking about a different kind of momentum. We are going to be talking about angular momentum. So this one is linear, and we show it with P, and it's a vector quantity, so we better put the arrow on it. And it's defined by mass times, which is mass scalar, velocity, which is vector. And its unit is, you can work this out, this is kilogram, this is meter per second, so unit is kilogram times meter per second. So why is this interesting? Let's take a look at the change in momentum. And the way we look at this, okay, we can do average change and like instantaneous change, blah blah. We can just start with what we need. dp dt is equal to d dt times mv, and we are assuming the velocity, the mass is constant. There may be some problems, the mass is changing, but for this entire course, we will probably not have any problem with changing mass. So the only changing thing is velocity. So we can write this as like m dv dt, but m dv, like dv dt is, you know, it's acceleration, so this is equal to m times a. But from Newton's law, we know that this should be equal to sum over all external forces, which we demonstrate, which we represented with this form. So this is due to Newton's second law. Okay. So this way we have like actually a new and like I think sometimes a more general form of writing Newton's second law. I think this is also how Newton wrote his second law. This was sum over all external forces is equal to change in momentum. So if you have more than one constituent in your system, for example, if you have more than one body, if you have, say, 2 blocks or 2 different cars, things like that, the momentum is just like a linear sum of individual momentums. So like total momentum is obtained by vector sums. And what this means is, like, say if you have 2 different pieces of your system, total momentum is P1 plus P2. And if you have more, you can add more. Now we can talk about conservation of momentum. So let's write it. So if the total force is 0, if no force, then the P dt should be 0, but this is the total dp dt. So we are saying the total momentum is conserved. So this is conservation of total momentum. And if you have these, like say, okay, if you have like a problem like this, two masses come in, I mean, there is no external force, they have the velocities, whatever they have, they collide and they go their own ways. So I can just say that, okay, the momentum is conserved, whether they collide or not, there is no external force. So I can set this problem up from the momentum point of view, and we can consider the collision with the, okay, momentum conservation. So, okay, something like that. Collision between, okay, here it's written like MA and MB. Let's use that notation. So MA and MB, and we know that momentum is conserved. So initially what I have is M1, M1, B1 is a vector, and plus, okay, let's use the same notation, MA, VA, MB, VB. And after the collision, I need to use a new letters for V and VA and VB. The way I do is like two primes. The masses are the same. I assume there's no breaking or like there's no like explosion. So just they come in one piece, go in one piece, MA times VA vector prime. That means the mass A has a prime velocity after the collision, and same for B and B, right? Simple stuff. And here's the example. So there's like railroad cars, and they collide, and they like a 10,000 kilogram railroad car A traveling at speed of 24.0 meter per second strikes an identical car B, which is at rest. If the cars lock together as a result of the collision, what is their common speed immediately after the collision? Okay, so I have some MA, let's call A because they are all the same mass, M times VA, and MB times VB, but you know VB is at rest, so it's 0. This is supposed to be equal to the mass after collision. This is, okay, let's write it like MA. So this is MA plus MB, and the velocity, let's call it V prime. And the question is asking us, what is their common speed immediately after collision? It is V prime should be equal to, okay, the masses are equal, so it's going to be equal to 1/2. Maybe I can write one more step. MA plus MB times VA, and this is 1/2 VA, and this should be equal to what? 12.0 meter per second. Okay, simple stuff. Any questions? All right, let's move on. Speaking about collisions, we can introduce something called impulse. And during the collision, of course, we said the external forces are zero, but each mass experiences a force due to the other mass. Of course, there are Newton's third law pairs, they're equal and opposite. But if you are focusing on just one mass, like say, if you are focusing on only one mass, there is a gigantic force coming from the other one. But the point is, the duration of this force is like very, very tiny. It happens almost instantaneously, right? They just collide and then just separate. And so time, okay, maybe I can write this. So during collision, maybe I can write it in a different way. Collision time is very short, but the force due to collision is big, right? And the way we describe this situation is by generally using something called impulse. So, okay, how do we, okay, maybe I can write this one too. Thus, introduce impulse to combine these like short time and big force. And the way we do this is like, okay, force is equal to, we said dp dt, then change in momentum, which is dp should be equal to force times dt. And if we have like a finite amount of time, we can write this, integrate both sides. Total change in momentum, which is a vector, should be equal to, from initial time to final time, integrate over t and the force. And we generally show this with some capital J, and we call this impulse. Okay. So the geometry is something like this. Actually, this is very smooth, but it is not. But it's like, think of this like a cartoon picture of what's going on. You have force versus time, and of course, there is no force before the collision because they are not in contact. And when they come in contact, there is like a spike of force, something like that. This is actually much sharper, but this is, like I said, a cartoon. And the time here, delta t, is very brief. So if you integrate this tiny interval with this gigantic force, you get the total change in momentum. And we can actually introduce something called average force, like average force. Force F average should be equal to this impulse from t initial to t final dt f, which is a function of time, and we can divide this by total time. Okay. Thank you. What can we say about delta t for train question? Yes, so for the train question, you may say they are in contact for a really long time, but once, okay, whether they are in contact or not doesn't matter, right? The amount of force, okay, this train comes in and bumps into this other train, and once they lock in, there's no more force between them. They are locked together. So the amount of time that there is a force on this train from this train is actually very brief, very, very brief. So this time is actually not the time they are in contact, right? That's a good point. Just because they are in contact doesn't mean you need to extend this time. They lock in and then the force is again Like they come in, bump into each other, and forces again a spike. Good question, thank you. All right, that's what it is. And finally, okay, what about the energy, right? We introduced energy and we said it was very useful last week. So there's also energy in collisions. And if the energy is conserved, we call them elastic collisions. And maybe, okay, maybe I can write it. Energy conservation. And of course, here we are only talking about kinetic energy. If you have like a potential, it can be a little bit more like in mole, but it's exactly the same logic. And the way we write this is like, okay, 1/2. Let's write the kinetic energy of the first one, and 1 v1 squared plus 1/2 to v2 squared should be equal to the same thing with primes, right? 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. Okay. Okay, this is for, I said, elastic collisions. And we need to combine this with momentum conservation because, you know, we also have like m1 v1 plus m2 v2 should be equal to m1 v1 prime plus m2 v2 prime. Okay, there is like, okay, you can do it any way you like, but the way I do this is I use the first one and I write it is like 1/2 m1 v1 square minus v1 prime squared should be equal to, okay, what I did is I took this guy to this side, and I'm going to take this guy to this side. Okay. So this is 1/2 m2 v2 prime squared minus v2 squared. Now I write this using like this squares. A squared minus b squared is a minus b times a plus b. So this is 1/2 m1 v1 minus v1 prime v1 plus v1 prime should be equal to 1/2 m2 v2 prime minus v2 and v2 plus v2 prime. But I can do exactly the same thing here on the momentum conservation. Okay, maybe I can separate these things so that you can compare. I'll put kinetic energies on one side like this. And I think this guy belongs to here. This guy is momentum conservation. Let's move it here. This is kinetic energy, let's move it here. So I can do exactly the same thing here. This is m1 v1 minus v1 prime should be equal to m2 v2 prime minus v2. Now I see I have m1 v1 prime v1 minus v1 prime, m1 v1 minus v1 prime. These are identical. And on the other one, on the other side, I have m2 v2 prime minus v2. I have m2 v2 prime minus v2. But these things are equal, so I can cancel these, right? Cancel that with this. Of course, 1/2, I can cancel that too. So what I find is v1 plus v1 prime should be equal to v2 plus v2 prime. Of course, this is in 1D. Okay. Any questions? Some manipulations, but I think simple stuff.
I think we wrote the second equation is wrong. V1 prime minus V1, I guess.
So this equation,
No, upper one.
this one.
Yes.
So okay, this is M1 V1, and I take this M1 V1 prime to this side. So this is M1 V1 minus V1 prime. But here V2 prime is plus, and I took the V2 to the other side, so the V2 without prime is minus. I think this is correct. So I think, and don't be confused, it's going to be M1 V1 minus V1 prime. On the other side, M2 V2 prime minus V2, right? Do you agree? I think it's a little bit
I agree with
bookkeeping.
you.
It may be confusing sometimes. So you keep your indices in your mind. Do not, like, sometimes I also tend to write V1 minus V1 prime, V2 minus V2 prime. So you have to be aware that this side is actually the opposite order. Good. All right. So here's an example. Let's solve a problem and see. A very common practical situation is that for a moving object, MA, to strike a second object, MB, the target, which is at rest, VB is equal to 0. Assume the objects have equal masses and that the collision is elastic and occurs along a line head-on. A drive coordinates for BB prime and BA prime in terms of initial velocity VA of mass MA and the masses MA and MB. And B determine the final velocities if moving object is much more massive than the target, and C determine the final velocity if the moving object is much less massive than the target. We're just going to look at the limits. So okay, let me go ahead and start. So I will, okay, maybe I can write. So the velocity, what we found was, okay, let me go back here and see what we had. All right. So first we start with this momentum conservation, right? Let me write it as like VA. Maybe I can write it from the beginning. What we have is MA VA plus MB BB should be equal to MA VA prime plus MB BB prime. And from the kinetic energy conservation, what we found is something like this. So we don't have to write the quadratic equation. We can just write this one. So this is VA plus VA prime should be equal to VB plus VB prime. And we want to write VA prime and VB prime in terms of VA and VB. Right? Of course, there are many ways to do this, but I think the way I do this is like to try to cancel sides. For example, I can write it is like I can take the first equation, VA minus VA prime, and there's an overall mass, and A here should be equal to MB VB prime minus VB. Maybe I can put MA here and cancel this, and I can sum these guys. Or actually, because I am trying to solve it for What am I trying to solve it for?
The initial velocity of B is 0 hocam.
But yeah, I don't want to put it. I want to keep it general. So I want to keep it general. So I want to write, okay. What I want to write is for you to like, I want to get a general thing. So something like VA prime is equal to something times VA plus something else times VB. And VB prime is equal to something times VA plus something else VB. I'm trying to solve this way. I think that's a little bit more general. I think I like it that way better. Okay, so here what I'll do. So this is what I want to get. Let me pull this down just a little bit. And from the other one, I have MA VA minus VA prime is equal to, I see, yes. MB VB prime minus VB. So if I multiply this one with MA both sides, so let me do this. This is MA both sides and sum these things. Now you know what I'm trying to do. I can delete this. So what I'll get is, okay, these two things will cancel. So this one will cancel with this one. And I'm going to have 2 MA VA is equal to, okay, what do I have on the other side? I have VB, so MA minus MB, so these guys, MA VB, MB VB, so MA minus, okay. So this is VB plus MA plus MB, MA plus MB, VB prime. All right, that's exactly what I wanted. And I want to solve this for VB prime. So VB prime should be equal to, so 2MA divided by MA plus MB times VA, that's exactly what I'm trying to get, plus MB, so I'm taking this guy on the other side and putting a minus sign in front, so it's going to be MB minus MA rather than MA minus MB. So, and divided this by MA plus MB times VB. All right, right? So I have something purely in terms of initial velocities and masses and VB prime. So I can do exactly the same thing for VA prime. So I think the way I would do this, I would just change anywhere I see A, I should just write B, right? Because I can change the indices of these equations. So this would be, okay, 2 times MB divided by MA plus MB times VB plus and MA minus MB divided by MA plus MB, and this is VA. So can you guys verify this? I think I wrote it by just looking at this equation, which is the reasonable thing to happen, but I think you should, maybe I can do exactly the same thing. So let me do this. So what I did to obtain the first one was, okay, let me start from the beginning. I said VA, okay. So let me write VA minus VA prime times MA should be equal to MB BB prime minus BB. And I try to cancel V8s. Now I will do exactly the same thing, but I'll try to cancel VB primes. And for that, I write VA plus VA prime should be equal to VB plus VB prime. And I multiply this side with MB, this side with MB. And I take the difference now. If I take the difference, so this guy will cancel with this guy, so VB prime will be eliminated, and I will have on this side MB times 2VB, and on this side I have MA plus MB times VA, right? MA VA and plus MB minus, okay, push this just a little bit, MB minus MA, right? Yes, VA prime, and I'm trying to solve it for VA prime. So we are subtracting, so sorry, this is, I did the subtraction, so this one will be minus, this one will be plus. So VA prime, now we can solve this. VMA minus MB divided by MA plus MB times VA plus 2 times MB divided by MA plus MB times VA, which is exactly what I wrote here. Okay, but if you want to verify this, you are doing exactly the same logic. Can I delete this? So I will delete that side if everybody agrees with that, because I want to do other things.
I can see why we say mass B sum of the velocities equal to mass B sum of the mass B velocities of mass B. Yes, that part.
This equation?
Yes, hocam.
So I obtained from the kinetic energy conservation this, right?
Right.
V1 plus V1 prime is equal to V2 plus V2 prime, and VA plus VA prime is equal to VB plus VB prime, and I multiplied both sides with VMB. That's the kinetic energy conservation. That's a very good question. Thank you. Right? That's the key point about this exercise. And here I did exactly the same thing. VA plus VA prime is equal to VB times VB prime, and I multiply both sides with MA. Here I multiply with both sides with MB. And if I use these two equations or these two equations, I solve it for VA prime or VB prime. You see, I get confused. I mean, I did this calculation maybe I don't know how many times. I got confused every time. So you better do it a couple of times.
But how we omit the masses in the first? Because
So this one?
Yes.
So I said, okay, from the kinetic energy conservation, I simplified and I got this equation. Do you agree with this? I can write this no matter what. V1 plus V1 prime is equal to V2 plus V2 prime. Do you agree with this result?
And I don't understand that part, hocam.
So,
Because...
okay. So what I did was like kinetic energy is conserved. So 1/2 m1 V1 square plus 1/2 m2 V2.
Yes,
So,
yes.
and on the other side, I have V1 primes. And I said, okay, let me take this V1 prime to this side. And I wrote is like V1 squared minus V1 prime squared. And on the other side, I had V2 prime squared minus V2 squared.
I see
I
now.
use it like a minus, okay, I used a square minus b square is equal to a minus b times a plus b. And when I wrote it like this, I found that there's actually a piece that's exactly coming from the momentum conservation, right? There was like m1 times v1 minus v1 prime and m2 times v2 prime minus v2. And if I started with momentum conservation, I got exactly the same piece and I canceled those. So at the end, so my point is I don't want to deal with this quadratic v squared. That is a little bit nasty. So I reduce it to something linear, v1 plus v1 prime, v2 plus v2 prime. Since this was general, I can forget about kinetic energy anymore. I can just write this one. And that's what I'm doing here. So I started with momentum conservation. And I wrote VA plus VA prime is equal to VB plus VB prime. And I multiply both sides with MA here and both sides with MB here. And I try to solve these equations in parallel. But I think, like I said, this is not like a simple like you can do your eyes closed. You have to do it a couple of times to get the muscle memory.
Thanks, hocam.
All right. Any other questions or objections? And like I said, this one is general, right? This is one-dimensional collision. No matter what VA, VB, MA, MB, this equation is correct. So it should be 2 MB VB. I'm not sure which part you are referring, but if you think there is something wrong, we can like fix it. All right, so this is derived equations for VB prime, VA prime in terms of initial velocity VA, MA, and mass is MA, MB. Okay, so if you set what VB is equal to 0, set VB is equal to 0, then VB prime is equal to 2MA divided by MA plus MB times VA, because VB is 0, and VA prime is equal to MA minus MB divided by MA plus MB VA. Okay, everything is only written in terms of VA. So that's what the question is asking. And B, determine the final velocities if the moving object is much more massive than target. Okay. So this one was A. So B, if MA is much larger than MB. So MA is much larger than MB. So, okay, here I have something like MA. So if MA is much larger than MB, I can forget about this term. Just cancel that. So then B prime is going to be equal to 2MA divided by MA is equal to 2 times VA. And VA prime is going to be equal to, okay, if MA is much larger, okay, forget about that. VA is basically unchanged. Right? That actually makes a lot of sense to me because you collide with A, so and B is stationary. B goes with twice the velocity of A, and A does not change its velocity at all. And C and B is much larger than MA. This one is a little easier to understand because it is kind of like, okay, MA is coming, MB is kind of like a wall because it doesn't change. And we expect the velocity to change its direction. Let's see if this is the case. So VB prime is equal to, so we are trying to put MB much larger than MA. If MB is much larger, so this thing will cancel because you have a very large denominator. This thing is going to be 0. So VB prime is 0. and V A prime is going to be equal to, okay, MB is much larger, cancel that, but there's like a overall minus, so VA is going to be equal to minus, VA prime is going to be equal to minus VA. So this is exactly the situation. You come with positive velocity, you go with negative velocity, exactly as if you collided with a wall. Okay, this is like a collision with wall. Any questions? So okay, the question is asking us this part, but we did something more complicated, and hopefully you appreciate that because you see everything is much simpler, and this thing is general. No matter what collision you have in 1D, you have to deal with this one. If you want, you can memorize this result or write it somewhere and use it. So here's another kind of collision. So we said if the collision is elastic, the kinetic energy was conserved, but that's not necessarily the case all the time. So if the kinetic energy is not conserved, we call them inelastic. So this is collisions where no kinetic energy is conserved. Of course, the total energy is still conserved, but they are not like mechanical energies. So maybe I can write it. Total energy is always conserved, but it may be maybe it is converted to something like heat energy, which is not mechanically accessible anymore. But some is converted to heat, etc. Okay. And a special case of this inelastic collision is, maybe I can write it like here. Another bullet. This one is another bullet. So if objects stick together after collision, we call this completely inelastic. Okay. Why completely? I don't know. That's just I think for me it's just a name. But when people say like it's completely inelastic, that's what they mean. They stick together. Okay. Which actually makes sometimes this problem simpler. And here's the example. A ballistic pendulum. A ballistic pendulum is a device used to measure the speed of a projectile, such as a bullet. The projectile of mass m is fired into a large block of wood or other material of mass m, which is suspended like a pendulum, like here. And usually m is somewhat greater than m. As a result of the collision, the pendulum and projectile together swing up to a maximum height of h, like something like this, and determine the relationship between the initial horizontal speed of the projectile and v and the maximum height h. Okay. So like we said, momentum is conserved and only momentum is conserved. So m times v is going to be equal to, after the collision, the mass is combined. So it's going to be m plus m times v prime. Then v prime is equal to m divided by m plus m times v. Now the collision happened, and we can forget about collision now. You have this initial kinetic energy, E prime, and how much the block will rise, right? And how much the block will rise is determined by the kinetic energy conservation after the collision. So this is going to be 1/2 mv squared, but m is m plus m, and v squared is m plus, okay, this is, maybe I can write m squared divided by m plus m squared v squared. This thing should be equal to mgh. M is m plus m, g is g, and h is h. And say we are trying to find h in terms of this. Okay, let's cancel that. Maybe I can show more explicitly. Cancel this with this. And I found something like this. H is equal to 1/2. Actually, we are trying to determine v in terms of h. So because v is the unknown, let's write it in for v. V is equal to 2 times g times h root, and multiply this whole thing with m plus m divided by m. Okay, maybe it's a little bit more natural to write the factor in front this way. Any questions? So let's move on. So the collisions so far I considered were like in 1D, but there's, there may be cases where the collision is in a more general geometry, in 2D or in full 3-dimensional geometry. So the idea is, I mean, if the momentum is conserved, if momentum is conserved, which is the case in collisions, each component is conserved separately. So what this means is, like, suppose you have a collision like this, MA comes in, there's like a target which is stationary at first, and this guy bumps into this guy and they go their own ways. And there is no there's no breaking up. So MA is MA, MB is MB after the collision. So we can write, so along X axis, so MA, so I need to specify now velocities in terms of their components. So MA times VAX prime plus MB times VB, okay, VB, hopefully you know what I mean, VBX prime should be equal to MA VAX plus MB VBX. And for y-axis, I can write the same thing, MA VAY prime plus MB VB y prime should be equal to MA VAY plus MB VB y. And this, we said for this problem, at least initially B is addressed, so you can forget about this. This is 0, and I think VB, this is also 0, right? And your task is to solve this problem primes in terms of these guys. And if we are talking about elastic collision. If collision is elastic, you have 1/2 ma ba squared plus 1/2 mb bb squared. We know v squared is like a scalar now, and kinetic energy is scalar, so I didn't put vectors here. This should be equal to 1/2 ma ba prime squared plus 1/2 mb bb prime squared. But we said b is initially addressed, so this is going to be 0 as well. All right. Maybe an example may be helpful. Here's example 12 from your book. The billiard ball collision in 2D. A billiard ball A moving with speed VA in x direction strikes an equal mass billiard B initially addressed. And the two balls are observed to move off at 45 degrees to the x-axis. Ball A above x-axis and ball B below. That is, theta A prime is 45, theta B prime is minus 45. What are the speeds of the two balls after the collision? Okay. Let's consider. So we said x and y axes are considered separately. I think it's a little bit more reasonable to consider dy because it's initially 0. So I would say ma and va prime times sine 45, which is root over 2, should be equal to mb times vb prime root 2 over 2. Okay. I said this momentum, okay, maybe I can show it. So this momentum, I said, should be equal to this momentum. That's what this equation is. Any problems with that? So since the velocity, the masses are the same, so let's cancel masses because these are identical billiard balls. Roots cancel. So from here, what we obtain is VA prime is equal to VB prime. Now I can think about, okay, this one was y axis. Now I can think about x axis. And for initial momentum, I have m times A should be equal to m times VA times cosine 45, which is the 2 over 2, plus m times, but VB is equal to VA, so let's put it, okay, this is prime, VA prime, they are identical, and this is root 2 over 2. So cancel m's. What I find from here is, okay, root 2 the A prime is equal to VA, so VA prime is equal to 1 over root 2 VA. Yeah, I didn't mess up. Okay. And let's put the numbers. It says, okay, what are the speeds of two balls after the collision? So initially it is like 3 meters per second, and if you multiply it with 1 over root 2, I found something like, what did I find? Let me see. 2.1 meter per second. I found something like 2.1 meter per second. If VA is equal to 3.0 meter per second. Okay. All right. Let's move on. Now I want to introduce something called center of mass, right? Like so far we have been treating masses as if they are like point objects, right? You had like a giant block and we just put a dot for this block. Like you had like a block, and we just put the dot for the block and we treated everything as if they are like a point objects. If you had like an extended object, we put a point and or like something like that, right? You had giant object, we put a point for the center of mass. So actually we could do that because of this thing called center of mass. And if you look at the motion of these extended objects, and if you calculate their center of mass and keep track of their center of mass rather than this extended object like this jumper, like this diver, you'll find out the center of mass actually moves exactly like a point we described. It is exactly like a point mass that we treated so far. Okay. So here, okay, maybe first a warning. So this is different from center of gravity. Okay. So what is center of gravity? In like very briefly, if you have Earth, let's say, and if you have such a large object, the gravity acting here is different from acting here, right? That means the object is so large, we have to think about this m over r squared kind of force. And the question then boils down to what is this individual point that this gravity acts as if it's like a point mass. It's a different point. So we are talking about center of mass, not center of gravity. So that's just a small remark to keep in mind. And the definition of center of mass is like we said, again, extended object moves like a point object around, or not around, it's actually at exactly its center of mass. Okay, so that's the whole idea of center of mass. And the question is, how do I calculate the center of mass, right? Now, calculation. Suppose, like, let's simplify rather than this extended object. Let's start with two masses, MA and MB. And I'd like to ask, what is the center of mass? And center of mass is kind of like putting this thing in a balance. So what is the mass that I should put in some location X center of mass that's equal to some of these MA and MB, right? So the question is, how can I put a mass of MA plus MB in which position such that the problem will be identical with this one? And the way to set up is this, like, a little bit simple, and it's kind of like XA times MA plus XB times MB should be equal to total mass MA plus MB, and then X center of mass, which is the unknown, right? I can easily solve this for X center of mass. X center of mass should be equal to, what is it? MA divided by MA plus MB times XA plus MB divided by MA plus B times XB. So if you have many particles, you basically have exactly the same thing. You just need to sum over all of them, right? X center of mass is equal to 1 over sum over all masses multiplied with sum over all coordinates multiplied with masses. Okay. And it doesn't even have to be in 1D, right? So in, for example, 3D, you can think of some R center of mass, which is going to be equal to exactly the same thing. Sum over all I R I. Sorry, what am I doing? This is MI. Oops. So this is MI, sum over all masses and sum over all coordinates. But this time Ri is a vector times MI. Okay. So on the left-hand side, you have a vector. On the right-hand side, you have a sum of vectors, which is a vector. So this means you can do it for each component, right? For X component, for example, a center of mass is equal to 1 over total. Let's write it M for short, and maybe MT to remind us it's total. It's going to be equal to sum of I, Xi, Mi, and Y center of mass is going to be equal to 1 over M total, sum over all I, Yi, Mi, and Z center of mass is going to be equal to 1 over M total, sum over all I, Zi, Mi. And finally, if you have like a system, okay, they don't have to be discrete. They can be a continuum, right? Like this thing. So far in this problem and here, we are thinking about like individual masses randomly spread in space, but we can have like continuum of masses. So let me consider that. For continuum, of course, it's also like sums will just be converted to integrals. That's what the difference is, right? And for continuum, R center of mass is going to be equal to 1 over M total and sum over all little masses. Now these little masses are like infinitesimal, so it's like an integral times position of this little mass. So you consider some little mass, has some position, and you integrate over all volume. And this is like volume of the mass. Good. Any questions? Any objections? So the last part is just like exactly like this. Right? I'm writing exactly like this, but for like a continuum, right? So there are like infinitely many particles and they are infinitely close to each other. That's exactly the definition of integral. I just say, okay, this is my mass. I look at this individual thing and I sum over all of them. And this discrete index turns into this differential in the integral, and I integrate over the m times its position. And if I divide everything with total mass, that's my center of mass. It's complicated, but it's not. I think integral is like a psychological barrier for a lot of people, so I think should get used to that. I think maybe we can solve a couple of problems to see how this works. All right, so here's the problem. Show that the center of mass of a uniform rod, so initially this is like uniform, that means density is the same everywhere. Uniform thin rod of length L and mass M is at its center. We are trying to find that center of mass for uniform rod is its center. And this is one-dimensional. Okay, let me go ahead and start. A, what did we say? The center of mass should be equal to 1 over total mass, which is M, integral over all little masses and their coordinates, but this is 1D, so let's put it X. So the geometry is something like this. I choose just a little bit of chunk, and this I call it dm, and its coordinate is X, so I put X here. And now I want to write this dm in terms of X because it's a reasonable integration variable. So for that I use, because this is uniform, this is lambda times dx. And lambda is equal to total mass divided by length. Okay. So this is going to be equal to 1 over m. Let me put lambda outside. This is m over l integral dx times x. And limits of integral x goes from 0. So this x is 0 here. Or if you take the maximum, it's going to be L. So this goes from 0 to L. So this thing is going to be equal to 1 over m over L. And this integral is 1/2 x squared. Okay. Maybe I can do it here, 1/2 x squared, put the limits from 0 to L. It's going to be equal to 1/2 L squared. Clear this. Some cancellations, and this is going to be L over 2. So this is the midpoint as expected. And B, determine the center of mass of the rod, assuming its linear mass density lambda, its mass per unit length, varies linearly from lambda is equal to lambda 0 at the end of the end to double the value lambda is equal to 2 lambda 0 at the right end. Okay. So if you plot something like that, density versus position, so this let's call this rho or maybe lambda because it's one-dimensional. So the density varies something like that. And they are saying that this point is lambda 0 and this point is what? It's 2 lambda 0. Yeah, I need to find lambda 0 because it's like a parameter at that point, at this moment. So total mass should be equal to sum over all masses, and this should be equal to the x times this lambda of x. And what is lambda of x? Lambda of x is, okay, it's increasing linearly, so I can just write it like a plus b x. For x0, lambda is lambda 0, then a is equal to lambda 0. And for x is equal to L, lambda is equal to 2 lambda 0. So lambda 0 plus b times L is equal to 2 lambda 0. Then, okay, b is equal to lambda 0 divided by L, right? So let me write that. This is lambda 0 dx. Maybe I can write it here. Lambda of x is equal to lambda 0 1 plus x over L. So let's check that. If I put x is equal to 0, I have lambda 0. If I put x is equal to L, I have 2 lambda 0. That checks. And this is 1 plus x over L. Let's clear this part. And so I need to integrate this. This is going to be lambda 0. So this is x from 0 to L plus 1 over 2L x squared from 0 to L. And this should be equal to what? Lambda 0 times L plus 1 over 2L times L squared. And cancel this with that. I found something like lambda 0 times L plus L over 2, 3L over 2. Then lambda 0 should be equal to 2m divided by 3L. Now I can calculate x center of mass. X center of mass is going to be equal to total mass dm times x. This is going to be 1 over m. This is dx. So lambda 0 times 1 plus x over L times x. And if I calculate this integral, I have 1 over m to m over 3L. And I have the first integral will give me 1/2 L squared. I just multiply this and then take the square, 1/2 L squared plus 1/3 L cube. So cancel that with this. This is L squared. So this is going to be equal to 1 over m to m over 3L times 1 over 2 plus 1 over 3 is 5 over 6 L squared. So cancel m with m, L with L, like this one with this one, 3. If I didn't mess up, I found something like 5 over 9 times L. Okay. So what this means is, okay, initially it was right, the midpoint, now it's shifted a little bit, right? Because 5 over 9 is a little bit closer to this side than this side, which makes sense. Maybe I can write shift to right. Any questions for this exercise?
In the A part, instead of dm, we wrote lambda times dx. Can you tell that part again?
So it is, okay, dm is like this infinitesimal mass. And mass is by definition the density of mass, which is lambda, times length. But here the length is dx, right? So I said dm, this infinitesimal mass, is infinitesimal length times the density at that point. But the density at that point was uniform in part A. So I put m over L for density. I did exactly the same thing for part B. The m is equal to dx times the density at that point. And now the density at that point was determined with this equation. And I found lambda 0 here. Here, the same trick, dm is equal to length, this infinitesimal length, times the density, but the density is this lambda 0 times 1 plus x over L, and this x is this x. Is that clear?
So lambda is m divided by L everywhere, right?
Yes.
Okay.
But the point is, sometimes it's not uniform, right? So if it is not uniform, you need to find lambda in terms of like the little dm over dx. Okay, right? That's clear, right? So this little, okay, lambda is total mass in this little chunk, which we show with dm, and you need to divide it by little x dx. And it may or may not be the same everywhere, right? For example, in the second part, it's increasing linearly. So we found lambda from the total mass. We said the total mass is equal to m, and we said integrate over all m's, then this should be total m. And I set up the integral here, and I found it something like this. So m was equal to lambda 0 times 3l over 2, and I solved it for lambda 0, so it was 2m over l. For A, it was like uniform, right? For A, it was total mass divided by total length. It was much simpler. I didn't have to deal with nasty integral. So here, okay, we have about some time. So I want to like combine this center of mass concept with the translational motion. Oops. So I wrote, okay, let me start from here. So I wrote something like this. So let me remind you, this our center of mass was equal to 1 over total mass and multiplied with all over all I m I r I. And let's see how this thing changes with time, right? And let's take first derivative. Okay. So on this side, take first derivative. So d r center of mass divided by t should be equal to okay, let's put m on this side because I don't want to write it there. M times d r center of mass is equal to sum over all I. So I'll act the derivative in each term in this sum. There's like sum a plus b plus c. I'm going to act the derivative on each term separately. So, and I'm assuming the mass is constant, so it's going to be equal to mi times dri dt. So I can do the same thing. So take the second derivative. So m again, d square r center of mass, divide this by dt squared is equal to sum over, again, I can act it term by term. So this is I mi d square ri divided by dt squared. But now this is, I know what this thing is. For example, this one was sum over all I mi bi, and this one is sum over all I mi ai. But I know the Newton's laws. Newton's law says this is equal to force acting on height mass. Then this should be equal to okay, maybe I can write in a new lane, and this is equal to m times, of course, this side is the acceleration of center of mass. A center of mass as a vector should be equal to sum over all forces acting on system. Okay. Now I want to do the following. Let's separate external and internal forces. So what this means is I have a distribution of masses, like say something like that. and take any mass, for example, let's take this one. Oops. Let's take this one 1 and this one 2. There's a force on 1 by 2, and there's of course a pair by Newton's law. There's like a force on 2 by 1. So let's separate these forces. And the way I do this is, so sum over all I should be equal to sum over all I external plus sum over all I Fi, let me call this internal. But I said, like for each internal force, there is an equal and opposite of its pair, right? So if you sum over all of these individual pairs, this internal is going to be 0. Okay, this is a little bit not readable. This is internal 0 due to Newton's third. So what I find is m times a central, okay, a central mass is equal to sum over all forces, external forces acting on each mass. Okay, good. So I can do the same thing for, like, for example, momentum. I can define P center of mass, which is going to be equal to sum of all momentums. And if I take its derivative, P center of mass divided by T, with the same logic, it's going to be equal to sum of all external forces from the system. So this is also Newton's second law for system of particles. So the key is, like, you separate a system to its individual components, and these internal forces always cancel, and what you end up with is this sum over external forces. Then you can think about this external force and then study Newton's equations, which is very convenient. And you can, of course, write it in terms of momentum language, because m times a is like dp dt in more general sense, and this is also equal to sum over external forces. So we don't have to worry about internal affairs. Okay? Any questions? All right, I think that's ends. So tomorrow I have how many problems? 1, 2, 3, 4 problems. Today I'm done. If you want to leave, feel free to do that. If you have questions, we can talk about your questions. Thanks for coming. See you tomorrow.